I've been with Excel for a year and a half. I primarily work on our internal search database, which is also a multi-database, and a bunch of infrastructure. So today we'll be talking about upscale search in Excel. So what are we going to talk about today? First, we'll go over some background on the entire system, what it does, and different components of it. Then we'll dive a little deeper into the vector search pipeline, what are the requirements of it, how it works, some of the optimizations we did, and finally, just look at some other small examples of optimizations we did recently that had huge impacts. But yeah, interesting examples. Yeah. So the database we built is called Alice, and it started out as a pure embedding search. And as we grew, we managed some bottlenecks and added hybrid search to address some of the drawbacks of embedding search. And we also added embeddings code for updates and deletes because we want to keep things fresh. Yeah, that's, I guess, how Alice evolved since it started out as just a vector search engine. And Alice has two main parts. There's a storage engine, which deals with taking some data, storing it reliably, making sure files are uncorrupted, ingesting at, I don't know, millions of rows a second. And then there's a query engine, which is where a lot of the fun performance optimizations happen. The query engine is just responsible for taking a user's query and returning the most relevant documents to that query, either using embeddings, V25, whatever algorithm you pick. Okay, so looking closer into the vector search pipeline, what are the requirements of the system, right? We want to support tens of billions of documents. We want efficient metadata filtering, so we want to be able to say, only give me documents in the last week, last month, last year, or only give me documents within these domains, or that contain only these phrases, right? And we want to be able to do this at hundreds of thousands of queries per second, because we have a lot of customers. And we want to do this in less than 150 milliseconds end to end. So if you think about how to do vector search naively, right? If you just load all your embeddings into memory and do a naive dot product, that's extremely slow. It's possible, but extremely slow and extremely expensive. Some quick napkin math, if you had each embedding was 4 kilobytes and you had a billion embeddings, that's 4 terabytes of memory, which is a lot. So we want ways to compress this so that it wants less memory, and also means use less memory bandwidth and fewer flops to actually compute the semantic scopes. So the first thing we do is the time reduction. So we have this big embedding, say 2048 dimensions, and we want to compress it to smaller embedding. There are many techniques to do this, but we train our own embedding models, so we train the embeddings to be Matryoshka embeddings. And what that essentially means is you can simply truncate the embedding and still maintain a valid representation of the document you're embedding. So you take your original large 2040 dimension embedding and you simply truncate in the first 56 dimensions, and it's still a valid representation that you can use to search. And that reduces the memory, again, I come out 2048 to 256 by roughly 8x. So you go from 4 terabytes to 512 gigabytes of memory, which is still quite a good amount, but it's still way better than 4 terabytes, right? So that's the first thing we do. The second thing we do is something called binary quantization. So by default, these embeddings store all these numbers or values in B416, and what that means is each dimension takes 16 bits of space, and the total space per embedding is just our dimensions times bits per value. So something we do is we compress each dimension from floating point values to binary values. So 1 and -1, and how we do that is essentially we just check if the number is greater than or less than 0 and compress it. Turns out this works kind of well, better than you'd expect, I guess. And yeah, that reduces the memory further down by 16x more. Total for 128 memory reduction since we started. We're now at 32 gigabytes of memory, which fits up probably most people's laptops here. So yeah. And we release our memory, but it's still a brute force search over all embeddings. That means that we do a scan over every single document in the index. One final thing we do to reduce the search space is something called IVF. IVF is essentially doing k-means clustering over all our documents, partitioning the documents into different clusters, and only searching on the clusters, closest clusters to your query embedding. So you're doing a query embedding, say you have 100,000 clusters, you only search on the top 1%, 0.1% of 1% of clusters. And that just reduces the amount of compute you need by 100 or 1,000 fold, depending on what parameters you choose. So these three techniques all talk about elsewhere. We implement dimensionality reduction and IVF similar to how a lot of other vector databases implement it. But something we do differently is how we do binary quantization. And again, the algorithm is pretty simple. If I get a 0 then 1, I'll make it a 1. But what most people do is they do this for both the query and document embedding, and then take the Hamming distance between the two. And it turns out this doesn't scale that well when you have a lot of documents. You lose a lot of recall. And something we figured out was, what if we just compressed the document embedding and kept the query embedding as floating point values? Because that leads to no more memory usage, right? Query embedding is, we don't store that in memory except when computing it. And we just take regular dot product, and it turns out this is way better than what you get if you compress both. And you can also optimize, a lot using sync instructions, which we'll see in a second. And it's only around 2x slower than Hamming distance after all the optimizations, but way better recall. So yeah, this is a hybrid binary and float dot product. So if you don't like dot product, you're using doing regular floating point math, but you want to optimize that. How do we optimize that? One simple thing you can do is, suppose you have 8-dimensional embedding, right? You have 8 values. Split it into 2 chunks, 4 values each, or 4 dimensions each. And remember, those x's are only 1s and negative 1s, so only 2 possible values. So for each chunk, they can only choose the 4 possible values. So you can essentially pre-compute all possible scores for that sub-embedding and store them in the lookup table. And you can cache the computations. So instead of having to compute a dot product every single time, you compute it once, you cache the result in a lookup table, and you can compute a dot product equally just looking up a value in the lookup table. And this essentially goes, if you didn't use a lookup table, in this case you need 8 multiply ops and 8 addition ops, I guess. And with lookups, you divide that by 4, so you only do 2 lookups here. So if your vector has d dimensions, the number of lookups essentially becomes d over 4 or d over 8, depending on how you split the vector. And one final thing we do to further optimize this is we use SIMD instructions. This lookup table is pretty small, right? If you only have 16 values, and each value is, say, for 16 bits, then you have 2d6-bit, your entire lookup table is 2d6 bits. We have a lot of SIMD registers available to us. On x86, for reference, you have 32 registers, and each register is 512 bits. So you can just store all these, this entire lookup table in registers, and use a class of instructions called shuffle or permeate instructions that essentially allows you to do lookups simultaneously, multiple lookups simultaneously, and get the results. One nice thing of x86 is, since the registers are so large, you can actually increase the size of the lookup table, thus reduce your instructions. So we end up using 8-dimensional subvectors instead of 4 dimensions, as shown in the previous slide. And something else, kind of fun fact, I guess, is when benchmarking those various machines, we found that AMD Zen 4 has roughly 2x the throughput on this one particular instruction we use compared to Intel Sapphire Rapids. Everything else, the same throughput, sometimes slightly less. But this one instruction, it has 2x more throughput. So AMD is like, at least this subpart, it's 2x faster than AMD than Intel, which is pretty crazy. Again, this is possible. I've been talking x86, 512-bit registers only on x86. You can do this in ARM, but ARM has fewer assembly registers and smaller registers. So you have only 16 registers instead of 32, and only 128 bits. Each register is only 128 bits instead of 512 bits. So you gotta reduce your subvectors 4 dimensions to be able to do this in ARM. Okay, so.
Right. Do you mind if I ask a question?
Yeah.
Yeah. So going back. So yeah, the SIMD optimizations are really cool, and being able to keep everything in registers is amazing. Are you not bottlenecked on bandwidth instead of arithmetic operations here?
We do become bottlenecked on bandwidth when we at scale.
Got it. Okay.
Yeah. After a certain a threshold, you do get bottlenecked bandwidth. It's so fast on Intel, but you do get bottlenecked bandwidth.
Got it. And so then you want to optimize data movement, so the binary quantization and all these. It's more about reducing the size of these things to reduce the memory bandwidth load.
Mm-hmm. If you do regular floating point ops, you don't become bandwidth at on CPUs. Not necessarily, but okay. Putting all this together, what does a pipeline look like? Pretty simple, pretty linear. You get a query embedding. You find the closest clusters or partitions you want to search over. Say like top 1% or 0.1% of the index. And within those clusters, you do a super approximate search using 2D 6-dimensional binary, using techniques we just talked about, with the SIMD optimizations and everything. And we get some candidate set. And then we take that candidate set and then we re-rank them with a less approximate embedding. So we do the same binary thing, but with more dimensions. And once we finish re-ranking that, we re-rank again with full 2028 dimensional floating point embeddings. And this multi-stage pipeline essentially allows us to recover the loss and recall you get from previous steps, and in the end, you recover a lot of what you lost. And yeah, that's the vector search pipeline. So a general lesson I've learned when building all these systems, or I don't know, past how many months, almost more than a year, is a useful tool is to simply make estimations early on, do the napkin math, and throw out possibilities. And doing this over and over just is an extremely useful tool. And people will tell you to profile your code, but people don't talk about this as often. And I think it's a super useful tool to have in your toolbelt. And one example of what this looks like is, say you have 100 million vectors, 512 bytes per vector. Your memory bound is 1 terabyte per second. And how many times can you read that index from memory into your compute unit? And the answer is super simple, right? It's 51 gigabytes divided by 1 terabyte divided by 51 gigabytes, so 20 times a second. And things of this nature allow you to figure out what ideas are bad super quickly. And yeah, it's just a useful tool to have. What's the point of this number? It allows you to figure out what a good bad size is if you were to run vector search on GPUs. First, to do this napkin math, you have to know your system. You didn't know what your memory bandwidth is. You didn't know how many flops are available. You didn't know how many IOPS your SSD has. And you can find this information generally on reference manuals or spec sheets, but very often, unfortunately, you don't find that. You don't find this information online, and you end up having to benchmark them. So learning to benchmark your systems often and get these numbers yourself is a useful skill to have. All of this can essentially be summarized into the saying estimate and reconcile. So estimate how good your system should be, and reconcile the difference between what your system is and what you estimate it should be. And in that process, you either learn something new about the system that you didn't know, some assumption you made that was wrong, or you just find something stupid in your system and you fix it, and now it's like way better. And yeah, estimate and reconcile. And you keep doing this in a loop, and you just improve performance. Okay, so I gave a similar talk a year ago, and since then we've grown. We've increased our adoption index by 20x. We're processing over 50 times queries per second. We 5x the number of engineers. And some things broke along the way. We fixed some things, and I just want to share some interesting examples of things we did, or performance engineering we did, I guess. And the first example is distributed k-means. So if you recollect, we do IVF, and IVF is just doing k-means on documents. And to do this, we used phase GPU. And once we reached a certain threshold of documents, we hit bottlenecks in phase. Phase doesn't support default 16s, and we started moving a lot. And it turns out phase also sends vectors from CPU host memory to GPUs. So now we have bottleneck by communication between GPU and CPU host memory. And phase simply stopped working for us. So we wrote a script, simple script using task distributed that scales across nodes. It scales across nodes pretty much infinitely. Actually, that's not true. Bound by how many centers you can store on a single GPU. But it scales horizontally, and for the foreseeable future, it's good enough. And it's a pretty simple script. Yeah. The other fun thing I found out about recently is something called huge pages. So by default, when you allocate memory, your operating system gives you memory in chunks of 4 kilobyte pages. What that essentially means in practice is, say you have an array that's 12 kilobytes, right? That 12 kilobyte array is possibly split into 3 chunks of 4 kilobyte pages. And every time you hit say you're scanning over that array. So you go from first element to the element at the final boundary. And every time you hit a boundary at 4 kilobytes or 8 kilobytes, you end up with something called a TLB miss. What is a TLB miss? And operating systems, or all processes use virtual memory. And every time you look up a memory address, you need to convert the virtual memory address to a physical memory address. And this lookup is cached in CPU. This lookup has a cache. There's a cache in your CPUs. And every time you hit this page boundary, you have a cache miss. And you waste 50 to 100 cycles waiting to get this value from main memory. And turns out this could lead to huge performance degradation. And the way to fix this is to use something called huge pages. So instead of allocating memory in 4 kilobyte chunks, you allocate memory in larger chunks. Could be 2 megabytes, could be larger, 1 gigabyte. And that led to a 40% improvement in one of our hot loops. And yeah, huge pages, right? One thing to note is that huge pages, there used to be a drawback to huge pages on older processors, because the size of your CPU cache for your TLB lookups was different based on page size on older processors. But on newer processors, you have the same number of entries for all page sizes. So there should be no difference on modern CPUs, unless you're using swap memory. But yeah, it's a default on TC-malloc, so switching to TC-malloc pretty much fixes it. Other final thing, nothing major. We created dedicated thread pools for all our I/O and CPU bound work, and this slightly improved our P50s, nothing too noticeable. But our P90s and P99s got significantly better because less context switching. Yeah, this will can be done on this side because not all big users are the same. Different requirements for different users and queries. Anyways, finally, I wanted to share some useful resources I found helpful throughout, on-time performance engineering. First is Matryoshka.info. It gives you a CPU instruction, throughput, latency, and various modern architectures. Second, Intel Intrinsics Guide. It gives you a list of SIMD instructions, and you can just look them up. You can find out what's available in your toolkit that you can use to improve performance of these systems. And the modal GPU glossary, good intro to CUDA, good reference material for learning about the CUDA programming model and how GPUs work. And there's a book called How to Study a Model by folks from DeepMind. And it's specific to TPUs and running transformers on TPUs, but there are a lot of general lessons you can take away from that book. And you kind of see the same pattern of deriving things from first principles and estimating and reconciling, and you learn to do that over and over. And how to scale a model, that's a great book. You should check it out. Finally, EXA is a very useful resource because a lot of the spec sheets are hard to find. They're like one PDF somewhere on some random place on the website, and Google rarely finds them. So when you look up something on EXA just is better at that. So EXA is great for finding spec sheets or info from niche sites. That's all of my talk, I guess. If you have any questions, reach out on Twitter. And if you found anything interesting, if you found anything we'll talk about really interesting, Yana's exit.as/careers. And questions.
Yeah, I found this really interesting, and I was just curious. Are you guys thinking about potentially building custom hardwares that can do vector searches? Just specialized vector search. I was just curious.
If you had 1,000 years, not right now, but if you had 1,000 years, maybe.
So at a couple points you mentioned possibly running this on GPUs. I'm curious if you could say a little bit about how that went. It does seem like you're going to be memory bandwidth bound pretty readily for this workload, and GPUs do have like HBM3E, but you could probably find a CPU that has similar high quality HBM, and you don't have to pay for the tensor cores, you know.
So the bottleneck does become top K when you do this on GPUs, but you can also you can figure out what batch size makes sense on GPUs, but also GPUs become better only at certain throughput. So if you're not utilizing all your flops, if you're not utilizing your GPUs don't make sense. They have higher base costs, and that's why we're slow on CPUs. GPUs likely, we still have work to do here, or research to do here, but they might make sense at certain scale.
And then one other question. So you mentioned switching over to like dedicated IO and CPU thread pools. Is that just like Tokyo, like the two thread pools there, or did you have to roll your own for some reason?
So one of the thread pools is Tokyo, the other one is Rayon, we do all CPU work in Rayon thread pool. We spawn tasks onto the thread pool, and then the other one is Tokyo.
I have many questions, but is EXA basically massive rack? And so you retrieve some documents and they are then later sent to some language model. That's my first question. If you could elaborate on the rack idea. And second question is, how do you get the embeddings? For example, do you get a single embedding for a web page, or do you chunk it? Which embedding model do you use, and so on?
So I engaged my question.
The rack. Is EXA basically retrieval augmented generation?
I see.
What happens after the retrieval part?
So the output of this system is listed documents. Documents are just links on the web, and you can inject this into your LLM. We can return those links directly on our main endpoint. We also have an answer endpoint that takes those links and generates an answer for you. But you have the flexibility to choose between the two. You can get the links directly if you want, or you can get the LLM output if you want, depending on which endpoint you use.
Okay, and the embeddings, so which model do you use? How do you
We
train?
train our own model, and we train our own embedding model, and do that with that, and no chunking right now.
That's right, good stuff.
Thank you for the presentation. Really impressive. And I think at the beginning, your CEO mentioned that you guys are using Lens internally. How does Lens fit into this workflow?
Lens is not used in this system. Lens is used in a bunch of our other data pipelines. On our calling side, content management side, yeah.
Hey there, a really great talk. One thing I haven't been able to quite put together is how your system scales. So it seems somewhere between linear and logarithmic, but I'm not 100% sure.
It's somewhere between square root and linear, between the two. Because IVF tend to, if you want to maintain recall, square root kind of works, but you might have to scale it a little bit. Somewhere in between. Yeah.
Somewhere around root n.
It is an empirical experiment. Like we haven't scaled much beyond. We don't know what recalling yet when you scale like 10x more documents.
Okay.
So it's an empirical experiment at scales.
Thank you.
So Shreyas, thank you for your speech, very impressive. And I have a question about if we take time machine and travel back, what's the main factor drives you to build your own vector DB instead of using existing ones in the market?
Customizability. Initially, cost and customizability. Initially, we built this because other ones didn't have features we wanted, especially with respect to filters. And if there were filters that were expensive, so we built our own for that reason. Right now, the things we still gain out of it mostly is customizability. Customer wants this particular kind of filter at this QPS. How can we optimize a lot of this? And we know the system end to end, so we know how to do that properly. Yeah. Not in the near future, but potentially.
Good question.
Hey, you had a really nice slide on the difference between when you gave this talk last year and now. And if you were to predict this talk in a year's time, what are the metrics that change and what will you have been targeting over the course of that year?
What do I think will change next year?
Yeah, what do you foresee being like the targets of what you're optimizing next?
So we talked about this before, but when you scale systems, at scale, different systems start to make more sense. Because there exist some systems where you get a higher base cost, but enough utilization, the unit cost becomes cheaper. So we might move away from the algorithms we currently use and onto different algorithms, on different hardware, depending on scale, if that makes sense.
Yeah, so presumably the metadata filtering you're talking about is pre-filtering, not post-filtering, right? Can you say a little bit about how you are able to do that efficiently? Is that like maybe the driving reason you choose IVF instead of HNSW? And yeah, what does that look like for an IVF index?
That is a driving reason why we chose IVF. It becomes much easier to implement. So you have, say, 100,000 clusters, right? You pick the top 1,000 clusters to search over. Instead of computing a pre-filter over every document in the index, you only compute it over values in those clusters. And if you don't have enough, you can recursively do this until you have enough, and then compute distances over those. And there's a natural sharding strategy in IVF. There's no, things are sharded, right? Things are partitioned. And you can shard your filters that way, but there is no natural sharding strategy in HSW graph-based methods. Yeah.
I think last question.
Yeah. I know in the last year you were talking about some of the big breakthroughs that you've made, right? What are some of which one of those breakthroughs were the hardest to get to, and how would you say you got to it? What was the process like?
Since last year or overall?
Since last year.
Since last year, on the Microsoft side, there have been no big breakthroughs, I guess. But we added hybrid search. We've done a bunch of work on that side. Tom on the team has done a bunch of work on that. He published a blog post on that. So you can read about that, I guess. Yeah, no breakthroughs on the Microsoft side.